Okay, so let's quickly start the session, right? So today is the fifth introduction session on design of steel structure. So during the last introduction session, we have started the tension members, where we have specifically learned about the net section and effective net section, right? Or the critical sections, which we call the critical section. How we can find one section is critical section or not, or out of many sections of bolting, which section will be the critical section. So we have learned all these things during the last introduction session. Now today, first what we learn today, we will learn how to calculate the design strength of this kind of tension member. So first of all, we will find out the design strength of tension member in bolted connection. Then we will go for welded connection. Then we will learn how to design this kind of members. Okay, so let's go step by step. So to understand the design strength of the tension member, we have to revisit the failure criteria of the tension member, right? So if we know the failure criteria of this kind of members, then we can easily find out the factors which will influence the design strength of this kind of members. So let's quickly revisit that concept. So what do we mean by say tension member? The tension members are subjected to axial tensile force or direct tensile force. So if we consider this section over here, so and we are applying the axial tensile load. So which kind of failure or which mode of failure can occur in this joint? So first thing for the solid plate, if we look at the solid portion, what can happen? This solid portion can get elongated and finally get failed by yielding. Secondly, what can happen? That here, if we consider any section over here where the bolting is there, what has happened there? So we have reduced the cross section by inserting or by providing the bolt hole. So this where we made the bolt hole, that means we have reduced the cross sectional area. That means there will be a tendency of rupture. So first thing, the yielding can occur, yielding of gross cross section. Second thing, the rupture can occur, or these members can fail by rupture. So firstly, yielding, when we can consider yielding as a failure, when you know the elongation is up to 10 to 15% of its original length, then we can call it yielding failure. First thing. Second thing, the rupture failure. And one more phenomena can occur in this kind of members. That is the block shear failure. So rupture, we know the rupture thing, how to calculate the design strength due to rupture of critical section for the plate section. But today we will learn how to calculate this rupture strength for the plate as well as for the angle section. Because when we design the tensor member, the unequal angle sections are generally used or mostly used cases. So one more phenomenon, what I said, the yielding, the rupture, and one more thing can happen in this kind of tensor members. Like look at this connection here. What is here? One gusset connected, one angle section is connected to the gusset. So you can consider it angle section, or you can consider it as a plate section. Like say for example, we have a gusset. So two phenomena can happen. Like sometimes we need to connect a plate with the gusset, sometimes we need to connect one you know angle section with the gusset. So we will learn, first try to understand what do we mean by say block shear failure. Okay, so we have four bolts here. Okay, and it is subjected to tensile and shear. So mostly this phenomena occurs when one tension member is subjected to shear along with tension. Not necessarily all the times that shear force will occur, but we need to check for the block shear failure, as this kind of shear failures are, you know, or this kind of failures are common phenomena for the tension members. So in block shear, what happens if we don't provide the, you know, end and edge distances properly? Then what will happen? You know, this section can start rupturing like this, and the whole block will separate out from this connection. The whole block will separate out from this connection. Whole block. Okay. So now think like this. Here, this is the connection between a gusset and a plate. This is a gusset and plate, and this is a gusset and a angle. Now I will elaborate these things on the later slides when we will understand the design strength due to block shear failure. Okay, so here what is happening? So if my load is applying like this, and this portion of block, like consider this portion of block is separated out from this section, or what can happen, or this type of phenomena also can occur, like we have plate here, and this entire block will come out from the section. So here if we see this thing, then we can see that this is the application of load. And if we see the cross section over here, this cross section, if we see that this cross section and this cross section, or here this cross section along 1 2 and along 3 4, if we see these cross sections, with respect to this cross section, this force is a shear force. That means this plane is called, we are called this plane as shear plane, and this plane, nothing like this is a plane and subjected to direct tension. What will happen? Obviously tension will occur, and this plane we call shear plane. So this kind of block shear failure will associated with two kind of planes. Just remember, two kind of plane, this block will come out, and two kind of planes we will have. One shear plane which is parallel to the application of load, and one is tension plane where, or this is the perpendicular to the application of load. So in this kind of block shear failure, what is happening? The entire block will come out. So when we will consider that entire block will come out, then we need to consider the failure, rupture failure of shear plane, and yielding of tension plane, yielding of shear plane, and rupture of tension plane. When we will calculate the block shear failure, we will learn this phenomena. So we have learned that this tension member can fail in either in yielding to rupture of critical section, and critical section, whom we call critical section, we know the section with less effective area, or less net area, or less net effective area. So basically the section which will have less cross sectional area, we call the critical section. And third thing can happen, just we have learned that block shear failure. Now we will learn step by step how to calculate the design strength due to yielding, due to rupture, and due to this block shear failure. So first thing, the yielding can occur. So the design strength, first thing, the design strength obviously governed by the yielding. So if we are designing some tension member, say we are designing some tension member, so here is a gusset plate and one plate is here, and this P, factored load, or T, tensile force, so let's denote it with T. T is applied. So obviously to make this joint safe, this applied force, that applied force should be less than your design tensile strength of this connection. Now how to calculate the design tensile strength of this connection, now we will learn. So first we learn that how this kind of tension member can fail. Now we will learn, out of this failure criteria, how we can find out the design strength. So first, failure due to yielding, so we need to calculate the design strength due to yielding of gross cross section. So due to yielding of gross cross section, already we have visited this clause and this formula many times. So from clause 6.2, what it says, if we have a solid plate with width where this width is B and the thickness is T, then the design strength due to yielding TDG we can express like AG Fy. What is that AG? That is the gross cross sectional area. So AG will be equals to B into T, that gross cross sectional area, into Fy. Why Fy? Because we are considering the yielding as a failure here. divided by gamma m naught, that is the partial factor of safety due to yielding. So the value of this gamma m naught is 1.1. So by this way we can calculate fast design strength of the tension member that is due to yielding. Now what is the second criteria for calculating the design strength? What was the second mode of failure? The second mode of failure was the failure due to rupture. So how to calculate the rupture strength? So for the plate sections, we have already calculated the rupture strength when we have designed the bolt, right? So for plate section, the rupture strength or the rupture strength due to, rupture or at critical section, we can find out like this: TDN is equals to 0.9 AN FU by gamma ml, right? What is AN? AN is the net area. Now what is the net area? So here look at this diagram. Here we have a plate of width B and thickness T, like it has a thickness T. So if we see the cross section over here, say AA, this cross section, this is gross cross section because we did not make any hole here. But if we look at the cross section 1 and 1, what is happening here? We made two holes over here. So obviously the cross section over 1 2 will be less than the cross section over here A. So the net area for chain bolting we have learn to how to calculate. It is easy thing: B minus N into D naught, how much or how many bolt hole we have made here, multiplied by T. This is for the chain bolting. Now for the staggered bolting, we have also seen that AN, how can we calculate the AN? For the staggered bolting, the first part for the chain bolting will remain same, B minus N D naught. Now for the staggered pitching, what is staggered pitching? This is nothing but the center to center distance between two consecutive bolts measured along the direction of applied load. So this is your staggered pitching PS. If you know the PS value and how many staggered pitching are there, you can calculate this summation of PSI square by 4. So we have practiced uh, example on the last class regarding how we can calculate the net and effective net area for the staggered boltings. Okay, so this is for the plate section. Now we have another section, that is the angle section. So how we can calculate the strength or design strength due to rupture at critical section due to that angle section. So before going to angle section, we have threaded rod. We can use the threaded rod as a tension member, like we have a suspension bridge. So over here maybe the cables may be made up with threaded rod. So for these cases, if we have the threaded rod, that means all this portion the thread is happening or the thread is made. Then for this case, the design tensile strength is calculated using that formula: TDN will be equals to 0.9 AN FU by gamma ml. Now ask me what should be the AN value. That will be the area or root area or net area of the threaded rod. Like for the bolts, for the root section we have another cross section ANB is equals to 0.78 pi by 4 into d square. Likewise, if we have a threaded rod and we know the pitch, we can calculate the root area of the threaded rod. Now come to the main portion, the angle section. What will happen in the angle section when the tensile load is applied? So angle section, we know that angle section has two legs, 1 and 2, and generally angle sections are denoted as like ISA, Indian standard angle section. Say for example 100. Say consider this example: 100 into 75 into 10. That means 100 means this is the width of one leg. Generally the larger leg or longer leg should be connected with the gusset. Now what is that 75? This is the width of outstanding leg, and this 10 is the thickness of this angle section. So when we use that angle section to make a tension member, what we generally do, one leg we connect with the gusset. You can see here that this leg, 100 leg, is connected over gusset, and if we see from this angle, we can see that this kind of plan view is there. Like this section is gusset is continue there, and here the angle is also continue here, and there the line of bolting is there. Now think or see carefully, this leg, this leg is connected to the gusset. That means my load is transferring to gusset to this leg, right? First, so this connected leg will reach the ultimate stress. But this outstanding leg, what is happening here? No direct load is applied. So first, the stress will transfer to this leg, then the stress will transfer from this leg to outstanding leg by some local, stress transfer phenomena. So what is happening here? Here within one cross section, we have different stress concentration. We have different stress concentration. The my connected leg will reach to ultimate strength, but my outstanding leg will reach up to the yield strength, because neither direct load is applied on this outstanding leg, nor any kind of folds are made on this leg. So this kind of stress, uneven stress distribution over the cross section of a angle section, we call shear lag effect. Shear lag effect. Now, from this discussion, we have learned that my connected leg will reach the ultimate stress, but this outstanding leg will reach up to the yield strength. So, while designing or while calculating the design strength due to rupture of critical section, we need to consider two phenomena. One phenomena is occurring with the connected leg, and one phenomena is occurring with the outstanding leg, with some effect we call the shear leg effect. So for the angle section, our code clause 6.3.3 says, for the angle section, the design tensile strength due to rupture of critical section will be 0.9 ANCFU by gamma ml plus beta into AGO Fy by gamma m. Now look this equation very carefully. This portion, what this portion says, what is ANC? What is ANC? On the last class we have learned what is ANC. This is nothing but the net area of the connected leg. That means this part dictates that my connected leg is reaching the ultimate stress. That's why we are using FU here. Now look at this portion. What is that AGO? AGO is the gross area of the outstanding leg, whatever my outstanding leg is, and FY. Why FY? Because we are considering that my outstanding leg will reach up to the yield strength. Why yield strength? Because neither direct load nor any hole are made within that portion. So with combination with two things, we can calculate the TDN. Like we can calculate the TDN is equals to directly 0.9 into AG, considering the gross cross sectional area. Gross, that means AG is equals to AGO plus ANC. That means the gross cross sectional area of the outstanding leg and net cross sectional area of the connected leg. But we are not doing like this. What we are doing, we are considering that the connected leg will reach up to the ultimate stress and my outstanding leg will reach up to the yield strength. And to cater or to counteract or to manage that shear leg effect, here one coefficient beta is provided. Now how we can calculate that value of beta? Why beta is provided here? Beta is provided here to cater this shear lag effect, to cater this shear lag effect. Now how we can calculate this beta value? So code says that to calculate the beta value, we have some formula. So first says that beta should be calculated like 1.4 minus 0.076 W by T, Fy by Fu, Bs by Lc. Now I will, one by one, will explain what these terminologies mean. So what is that W? What that W means, right? So here written width of the outstanding leg. Width of the outstanding leg. So if we have, let's say if we have a section, I say 100 into 75 into say 8. Now here what should be the value of W? W is the width of the outstanding leg. That means 75 mm. Here the 75 mm will be that width of this outstanding leg. Now what is that T? This is the thickness. So here we have considered 100 into 75 into 8. So 8 will be T. Now Fy and Fu, you know, Fy is the yield strength of the plate and or angle section, and Fu is the ultimate strength. Now what is BS? Now this is important thing. What is BS? BS is the shear leg length. That means how much portion is maximum affected by this shear lag effect. So how to calculate the BS value? So BS is generally taken as, for the welded connection, this is taken as from the center of the bolt to the end of the outstanding leg, this portion, the portion I have just marked, this portion. So how we can calculate the value of this portion? Quickly let calculate. So if this portion from the center of the bolt to the end of the angle section, center of the bolt to the end of the angle section, this is nothing but the edge distance, because my load is applying like here, and this is the edge distance. So if that is denoted by Wi, so if I need to come to center, so what will be this little value up to the center? Wi minus T by 2. Yes or no? Now I need to go from last to this center. So plus, what is the width of the outstanding leg? W minus T by 2. So this will be the value. So if we simplify this equation, what will come? W plus Wi minus T. So in code, the BS value is written as W plus Wi minus T. Now how it is coming, you can understand from this expression or from this explanation, how we can calculate the BS value. So for bolted connection, the BS value should be the length from this center of the bolt to the end of this, angle section. Now if welding is done, so for the welded connection, where the welding is used, to make the tension member, there the shear leg length will be the leg length of the outstanding leg, W, nothing but the W. Okay, so while we will calculate the design strength for bolted connection, we have to consider, or we have to calculate BS like this length from the center of the bolt to this, like W plus Wi minus T. And when we have to calculate the design strength due to welding connection, then we need to consider the value from the end of the outstanding leg, or simply we can say the width of the outstanding leg. Okay, so by this way we can calculate the beta value. But again, code says check your beta with this formula, like fu by fy, gamma m naught by gamma ml, and the beta value should be equal to or greater than 0.7. That means beta can have a minimum value of 0.7. How much? 0.7. Okay, so now we can calculate the beta value. If we know the beta value, now put all these things in this equation, we can calculate the design strength due to rupture of the critical section. So by this way we can calculate the design strength due to rupture of the critical section for single angle section. Now here, for the precise calculation, we can go for this. Now while we will design this kind of angle sections, then what will happen, that initially we don't know the size of the angle section. What should be the size? Will it be 100 into 75 into 8, or will it be 75 into 75 into 8? So we don't know. At the first step of the design, we don't know. So for primary sizing, for the primary sizing, code says when we don't know how many bolts are there, what should be the end distance, gauge distance, edge distance, or what should be the number of bolts, what should be the diameter of bolt, then we cannot find out the TDN value from this equation. Like, then for the primary sizing case, we can consider the TDN value is equals to alpha into AN FU by gamma ml. So this is a screenshot of this clause where this alpha value is depend upon the number of bolt for the bolted case, and for the welded case it becomes 0.8. So on the last class I have discussed, while calculating the net and effective net area for the angle section, I have discussed these things for and today's class also. This alpha value, if we have one or two bolts, if we have one or 2 bolts, then the alpha value will be 0.6. If we have 4 or more bolts, then the alpha value, or 3 bolts, if we have 3 bolts, then the alpha value will be 0.7. And if we have you know greater than equals to 4 bolts, then the alpha value will be 0.8. So we can easily calculate the alpha value, and an will be the net area of the total cross section. Net area of the total cross section, like first, for the primary sizing you just need to consider a hole, then just you need to calculate an like this, AGO plus ANC. So we will solve some problem where we can understand how to calculate these things. So for the welded connection, this alpha value will be 0.8. So for primary sizing, while initially we are selecting this member, we can calculate the design strength due to rupture of critical section of single angle section by this, where alpha value depend on the number of bolts. Like if we have 1 or 2 bolts, then alpha value will be 0.6. If we have 3 bolts, alpha value will be 0.7. And if we have 4 or more bolts, we have alpha value 0.8. Or for the welded connection also, we have alpha value of 0.8. Okay, so two things we have learned. First, the design strength due to TDG, due to yielding of gross cross section. Second thing, TDN, the design strength due to rupture of critical section. Now we have to understand the design strength due to block shear failure. So till now, do you have any questions? How we can calculate the design strength? So when we will solve one problem, this thing will get clear, more clear. Okay. So now the thing is how we can calculate the strength due to block shear failure. Okay. So for block shear failure, first, in block shear failure, what we have learned, that in block shear failure is associated with shear and tension plane. Okay. So firstly, we will learn the block shear failure for a plate section, and then we will learn for a angle section. So our code says that your block shear strength or block shear failure should be checked against two criteria. One, shear yielding and tension rupture. Secondly, shear rupture and tension yielding. Now I will decode these things for you, what that shear yielding and tension rupture and tension yielding and shear rupture means. So here the failure phenomena or failure process is given. For the plate section, generally we have two shear plane. Like if the load is applied here, then the plane which are parallel to the applied load we call the shear plane. So here for the plate section, what will be the shear plane? The plane along 1, 2 and 3, 4. What will be the tension plane? The plane perpendicular to the application of load. So this portion 2, 3, 2, 3 will be the tension plane. Now this kind of failure can occur when either this plane, this shear plane can rupture. That means that a shear plane will shear off. It reaches up to the ultimate strength, and this portion or the tensile part can yield. So shear plane can rupture or tensile plane can yield. Either the shear plane can get yield or the tension plane get ruptured. So two phenomena can occur. We don't know which will occur on this actual structure. So we have to check against that two things. That my shear plane can get yielded and tension plane get rupture. One case. Second case, the shear plane can get ruptured and the tension plane get yielded. Or simply we can say we have to consider first the rupture of the shear plane and yielding of the tension plane, and secondly the yielding of the shear plane and rupture of the tension plane. Now for the angle section, what is happening? So here Angle section, what do you know? Angle section have two legs, one is connected leg and one is outstanding leg. So here this portion shows your outstanding leg. So obviously the block shear failure occur like this will get cracked and this portion will have get, you know, tear out or yielded. Less, you know, chances that the failure occur along this side, because this side we have the outstanding leg. So obviously along this side there is a less chance of rupture. So now how we can calculate this thing? So first thing, we have learned that this kind of failure is associated with two plane. One is shear plane which is parallel to your applied load. Secondly, tension plane which is perpendicular to the applied load. Okay, now first, TDB is due to shear yielding and tension rupture. Shear yielding and tension rupture. That means we are considering that the shear plane is fail by yielding and the tension plane will fail by rupture. So look at this equation. First part, what is saying? AVG. What is that? AVG. AVG. That is the gross cross-sectional area along the shear plane. Gross cross-sectional area along the shear plane. So we are considering yielding along the shear plane. So obviously for considering the yielding, we need to consider the gross cross-sectional area. So for example, can you see this diagram? So if this distance is say for example, the center to center distance between two bolts is 50 mm and this, you know, end distance is 30 mm. Okay, so tell me what should be the value of AVG? VG, what I say, this is the gross cross sectional area along the shear plane. That means we have to consider this cross sectional area up to the center bolt and this gross cross sectional area up to the center of the bolt. So what will be the value of this for this case? What will be the value of this? 2 into 30 plus 50, this is the length, and say if I consider that the thickness, say for example T is 10 mm, so 10, that will be the gross cross sectional area along the shear plane. Yes or no? Do you have any confusion? Okay, now second part, what we are considering? Shear yielding and tension rupture. Tension plane get ruptured. Look at this. FU, we have reached up to FU, so this will be ML, not M naught, up to the ultimate strength, because we are considering the rupture. So tell me, what is that ATN? That is nothing but the, we are considering here rupture. So for calculating the rupture, we need to consider the net area, not the gross area. So what will be the net area for this case? If this distance is center to center distance, these two bolts, that means the gauge distance is say for example 40 mm. So tell me, what should be the ATN value for this case? Tell me, write it down. Tell me, what will be the value of ATN? Varun? The center to center distance between two bolt hole is 40 mm. That means my cross section is look like this. This distance is the 40 mm. And for example, this hole are say 22 mm holes. So what will be the net area? First tell me what will be the gross area. First tell me what will be the gross area along this tension plane. What will be the gross area without any bolt hole? So what will be that? Nothing but 40 into 10, if 10 is my thickness of the plate. Now what will be that thing is T or ATG. That means gross cross sectional area along the tension plane. Yes or no? Now what will be ATN? Net area. For calculating net area, half of the bolt portion we need to deduct from here and half of the bolt we need to deduct from here. So nothing but ATN will be equals to, tell me, 40 minus 22, 1 bolt hole. We need to deduct 1 bolt hole into 10. Yes or no? Now, second case, we need to consider the shear rupture. That means the shear plane get ruptured and the tension plane get yielded. So for rupture, we need to consider the net area and the ultimate tensile strength. So AVN, that AVN, that is the net area of the shear plane. So here the gross area of the shear plane is this 2 into 30 plus 50 into 10. What will be the net area? What will be the net area along the shear plane? So along the shear plane, we have one full bolt hole and half bolt hole here, because we are considering this length up to the center line, right? So what will be the ATN value for this case? For this case, ATN value will be 2 into 30 plus 50, that is the total length. Now I have to deduct the bolt hole. How many bolt hole are there? One and half, 1.5, because full bolt hole, one full bolt hole here and half bolt hole over here, because we are considering up to center line. So 1.5 into 22 multiplied by the thickness. Clear? So this thing will get clear when we will solve one example. So for the block shear strength, we need to consider two phenomena. One, first, the shear plane get yield or yielding in shear plane and rupture in tension plane. Secondly, rupture in shear plane and yielding at tension plane. So our TDB, the design strength due to block shear failure, will be minimum of these two. So I think you have some idea that how we can calculate this value. So let's quickly solve one example so that we can have better understanding. So what will be the design strength of the tension member? So the design strength of the tension member should be minimum of design strength due to yielding, because it can get fail by yielding, design strength due to rupture of critical section, and design strength due to block shear failure. So if I have a connection or tension connection or the tension member like this, and here the bolts are arranged like this, and someone says what should be the strength of this tension member or this uh, joint, or how much load this joint can safely transfer. So you need to calculate these three strength, then the minimum value out of this minimum value, that will be the design strength. Because if it fails by yielding, then yielding will be the failure for this case. If it let's say for example we find out that yielding strength is 40 say kilonewton, the rupture strength is say 45 kilonewton, and block shear strength is 50 kilonewton. So what will be the design strength? Obviously 40, because when we will reach beyond 40, this member will fail by yielding. Okay, so now let's quickly solve an example so that this thing get clear. Okay, so before going to problems, we need to check while we are designing or while we are dealing with the tension member, we need to check one more phenomena, that is the effective slenderness ratio, the maximum effective slenderness ratio which we can allow for the particular tension member. So here this is table 3 of IS 800, which says if a tension member in which reversal of direct stress occur due to load other than wind and seismic forces. So for this kind of member, we need to consider 180. A member subjected to compressive forces resulting only from the combination of wind and earthquake action. For this kind of connection, we need to consider 250. And most general case, a member normally acting as a tie in a roof truss. For these cases, we need to consider 350. And always in tension, the member always in tension other than pre-tension, that we need to consider 400. Like if we have this kind of member or trusses, now says like here we have a member. Now what should be the maximum slenderness ratio for this kind of member? So first you need to identify, is this member is subjected to direct tension or compression? What is that? Then according to that, means when you have found out that this member is subjected to direct tension, that means that maximum slenderness ratio will be 400. And what is that slenderness ratio means? Slenderness ratio means it is the effective length divided by least lateral dimension, that is equals to lambda max. Now if we equate these two, you can calculate length of the member or r minimum, how much radius of gyration you can give, all these things. Okay, so let's quickly solve the problem. So first we will solve the problem for the blade section, then we will solve problem for the angle section. So first problem says one plate, Indian standard flat plate of 130 into 12 mm is connected to a gusset plate by four number of 16 mm diameter of bolt. Okay, find out the design strength of the plate, where the plate is Fe410 and the yield strength of the plate is 250 MPa. So now what that example says, you need to find out the design tensile strength of this plate. So first you need to calculate, and we know that TDA or TD, more specifically the design tensile strength, will be equals to minimum of the three things: the design strength due to yielding of gross cross sectional area, the design strength due to rupture of critical section, and due to block shear failure. So we will calculate one by one. So first write it down, the given data. What is given? The diameter of bolt is given 16 mm. So 16 mm is the diameter of bolt. What should be the diameter of bolt hole for 16 mm bolt? And from table number 19 we have that for 16 mm bolt the standard clearance is 2 mm. So d naught will be 16 plus 2, that is equals to 18 mm. What will be the width of the plate? 130, thickness 12, and FUN of I is given. So first we need to calculate the design strength due to yielding of gross cross section. So from clause 6.2 we have the formula for yielding of gross cross sectional area, that says AGFY by gamma m naught. What will be the gross cross sectional area over here? 130 multiplied by your thickness. So 130 into 12, that will be the gross cross sectional area, multiplied by Fy, that is the yield strength, divided by factor of safety for the material failure considered in yielding. So this value comes as 354.54 kilonewton. Second, we need to consider, or we need to calculate the strength due to rupture of the critical section. So here the chain bolting is done, and the plate, here the connection is done between a gusset and a plate. So from clause 6.3.1 we can find out the TDN, the design tensile strength due to rupture at critical section, that says 0.9 AN Fu by gamma m. N is the net area, or we can say the area at the critical section. So here we have two sections, here 1 1 or 2 2. So two sections are symmetric because in both the sections we have two bolt holes, right? We have similar bolt hole. So we can calculate the AN. AN will be B minus 2 into D naught. D naught we have already calculated 18 multiplied by the thickness. The thickness was 12 mm. So AN comes out this, and if you plug these values 0.9 AN and FU value, the TDN value, the design strength due to rupture of critical section, comes as 332.98 kN. One more strength is left. So we have calculated TDG value, that comes as how much? 354. 354.54 kilonewton. And the TDN value comes as this. Now we need to check, or we have to calculate the design strength due to block shear failure. So third part, design strength due to block shear failure. So for this case the load is applied here. So obviously this is the connection between a gusset and a plate. This is your gusset and this is the plate. So here we have two shear planes, the planes parallel to the applied load. So 1 2 and 4 3 will be the shear plane, and 2 3 will be the tension plane. So first find this kind of problem are given. First calculate the value, first the gross cross sectional area along the shear plane, net cross sectional area along the shear plane, gross cross sectional area along the tension plane, and net cross sectional area along the tension plane. So how we can calculate here? So the end distance is given is 35, pitch distance is given 60. So what will be the value of AVG? That is the gross cross sectional area in shear plane. That means we need to calculate the area of 1 2 and 3, 4 gross cross sectional area without the bolt hole. So what will be that? So 2 multiplied by what is the distance from A end to the center of the bolt? 35 plus 60. So 35 plus 60 multiplied by 12. So this is your gross area AVG along the shear plane. Okay. What will be the net area along the shear plane? How many bolt hole we need to deduct here? Net area means we have to deduct the bolt hole here. So first bolt hole we need to deduct here and half bolt hole here. So like this, we have a section like here. So this is your 1 and this is your 2. So we need to consider from this to this without the bolt hole. So how many bolt hole we need to deduct over here? One full bolt hole and half bolt hole for this section. So total length 35 plus 60 minus 1.5 because one bolt hole for this section and this half bolt hole along this 2-3 plane. This comes as 1632 mm square. Okay. Now calculate the ATG, that is the gross cross sectional area along the tension plane. So what is the tension plane? The plane perpendicular to the applied load. So what is the plane perpendicular to the applied load here? That 2-3%. So what should be the gross area over here? Gross area with the bolt hole. Gross area. That means we have to consider the total area. So this distance is center to center distance is 60 mm. So 60 into 12. This will be the gross. Now what will be the net area? So net area will be, we need to deduct half bolt hole from here and half bolt hole from here. So this portion only. So 60 minus 1 into 80. 60 that is the total माइनस देखो यहाँ पे बोल्ट होल को अगर हम लोग नेग्लेक्ट करेंगे तो हाफ बोल्ट होल शुड बी नेग्लेक्टेड फ्रॉम दिस साइड एंड हाफ बोल्ट होल शुड बी नेग्लेक्टेड फ्रॉम दिस बोल्ट साइड. That means we will have one full bolt hole. That's why 1 into 18 is written here. Okay. So we have these values AVG, the gross cross sectional area along the shear plane, net 8ATN. This is the net cross sectional area along the shear plane and the gross and net cross sectional area along the tension plane. Now put these values in the equation. First, shear yielding and tension rupture. So for shear yielding, AVG Fy by root 3 gamma m naught. Look at this first part here, the shear plane, the yielding of the shear plane is considered, and here the rupture of the tension plane is considered. So here we have calculated out the values AVG, ATN, and that gamma m0 and gamma ml we can find out from table 5. So 1.1 and this is 1.25. If we put all these values in this equation, so first equation will give you that the shear yielding and tension rupture value will comes out as 447.95 kilonewton. Now we need to check for the second case where shear rupture, that means this plane, this 1, 2 and 3, 4, this two plane will get failure in rupture and this tension plane will get failure in yielding. So here TDB will be shear rupture and tension yielding. So you have the value of AVG, ATG, ATN, put all these values. So you will get for this kind of failure criteria, the design strength due to block shear failure comes out as 441. So what is the value? Minimum value here? Minimum value is shear rupture and tension yielding. Obviously, this phenomena is more occurring in this kind of connection. Like when you will pull these things, this portion will get ruptured first, and this portion will get yielded. So here the design strength due to block shear failure will be this. So first we have calculated the design strength due to yielding 354, design strength due to rupture of critical section 32.98, and the design strength due to block shear failure that comes out as 441.78. So what should be the design strength for this connection or for this plate? Will be the minimum of these three. So what is the value? This is the design strength due to rupture value. So this amount of load this tension member can carry safely. Clear? How we can find out the design strength for a plate section. Okay. Now quickly, do you have any question? Or we can solve another example also. This example is clear or not? Yes or no? Do you have any? Okay. So now, let's solve another example. Like where, staggered bolting is done. Here, one plate is connected with a gusset with staggered bolting. Now, how to calculate the design strength for this kind of joints? So tell me, in the staggered bolting, first thing, in kind of staggered bolting, the block shear failure phenomena will not occur. Look, if we pull this plate along this side, see, the bolts are arranged like in a manner that no block can come out directly. So for the diamond bolting, when we will calculate the design strength where staggered or diamond bolting is provided, then the block shear failure will not occur. So for this case, we need to find out just TDG value. That means the design strength due to gross cross-sectional area, and TDN, that is the rupture strength at the critical section. So first we need to find out the critical section. We have found out the critical section for this problem on the last class. Like for this kind of section, we can have the critical section 1 1. We can have the critical section like 1 2 2 1 1, or we can have a critical section like 1 2 3 2 1 1. So we need to check which section will have the minimum area or minimum net area. So what is given here? Write it down. The diameter of bolt is given. Diameter of bolt hole we can find out. For 16 bolt, the standard clearance is 2 The staggered pitching is given 40 The gauge is given 25 and for the plate width and thickness is given. So first we need to find out which section is the critical section. So on the last class we have found out that 1 1 section was the critical section because the net area along the 1 1 section will be less. So quickly go through that. So for 1 1, what will be the value of A net area? B minus ND naught into T, because it's a the 1 1 path. The 1 1 path is a chain bolting. So B minus ND naught into T. So how many bolt hole are there? 1, 2, 3 bolt hole are there. So 160 minus 3 into 18 into 8, right? So along the path 1 1, we have 848 square net area. Now, along the path 1, 2, 2, 1, what will be the net area? So, along the path 1, 2, 2, 1, we have staggered pitching. So, we have to consider this formula B minus ND naught plus summation of PSI square by 4G. So, along this path 1, 2, 2, 1, how many staggered pitching are there? 1, 2. 2 staggered pitching are there. And how many bolt hole are there? 1, 2, 3, 4 bolt hole are there. So 160 minus 4 into 18 plus summation of psi square. So how many psi are there? 1 and 2. So 2 into 40 square divided by 4 into g. What is the gauge distance here? Gauge distance is already provided, 25 So you can calculate the net area along path 1, 2, 2, 1. Now we have one more path left, 1, 2, 3, 2, 1. So along this path 1, 2, 1, 2, 3, 2, 1. How many bolt hole are there? 5. 1, 2, 3, 4, 5 bolt hole are there. So B minus 5 into 18 plus how many staggered pitching are there? 1, 2, 3, 4. 4 staggered pitching are there. So 4 into 40 square divided by 4. So this. So our 1 1 path or 1 1 section will be critical section, as 1 1 section will have the less effective area. So to calculate the design strength of this member, first we need to consider the design strength due to yielding of gross cross section. So yielding of gross cross section, we can calculate TDG is equals to AG Fy by gamma m naught, where AG is the gross cross sectional area. So 160 is the width and 8 is the thickness. So this is your AG portion total as a whole, and this is your Fy portion. Okay. So the design strength due to yielding we have from this formula. Now, what will be the design strength due to rupture at critical section? We know that our 1-1 section is the critical section. What was the AN for this 1-1 section? We have calculated the AN value 848 mm square. So put all these values 0.9 into AN into FU by 1. So the TDN value comes as 250.3 kilonewton. So what will be the design strength of the plate? Minimum of your TDG value. Minimum of what will be your TD value? TD value will be equals to minimum of your TDG value and TDN value. So what was your TDG value? How much you have calculated? 290. And what is the value of TDN? 250. So obviously the 250 will be the design strength of this kind of section. Now this was the calculation of design strength for the plate section. Why, or we can say to calculation of design strength of tension member where the plates are used as a tension member. Now angles, for the angles how we can calculate. So we have go through the equation from where we can calculate that TDN value for the angle section. So now quickly solve one example so that this concept will get clear. So here this example says we have a Indian standard angle section 19 to 16 to 6 is connected to 10 mm thick gusset plate. So this angle section is connected with this 10 mm thick gusset plate. This is your gusset and this is the angle section. So if we see from this side, we can have this plan view because this gusset is you know continued along this direction and this angle is also there and the bolts are made like this here. You can now visualize these things. So the angle is like this here. Yes. So this diagram is nothing but we are seeing from this side to get the plan view of the connection. Now says that 90 mm leg is connected to the gusset with gauge 50 mm. Okay. This distance is says 50 mm. This is denoted as Z, but this is nothing but if the load is applied on this direction, this is nothing but the edge distance. So 50 mm, this distance is given as 50 mm. Determine the design strength of the angle section. How we can calculate it? So first, what data is given? That I have to connect one ISA 90 into 60 into 6 and the diameter of bolt is given. Diameter of bolt hole we can calculate. The plate strengths are given, like ultimate strength of the plate is 410 and the yield strength of the plate is 250. So first we need to calculate the design strength due to yielding of gross cross section. So yielding of gross cross section, clause 6.2 says AG Fy by gamma m naught. Now what is that AG? That AG is the gross cross sectional area of the angle section. Gross cross sectional area or gross CS area. Now how we can calculate the gross cross sectional area? Either we can find out from SP6 directly or we can calculate from the angle section itself. Like we have angle section here. This is your 90 mm. The total leg length is 90 mm. This leg and this leg length is 60 mm. And the thickness is 6 mm. So what will be the gross cross sectional area of this leg? So we need to come up to the center line, because if we come up to this portion, here we have a overlap zone. That means we have more area. So first part, this is the gross area, so we need to come from the top to the center. This is the width. So 90 minus 6 by 2, that is nothing but we have come up to this section. Now for this leg, again we need to start from the center to the end. So 60 minus 6 by 2. This is the total width multiplied by 6. That will give us the gross cross-sectional area of the angle section. Multiplied by FU divided by 1.1. So by this way we can calculate the TDG value. So TDG, that is the design strength due to yielding of gross cross section. This comes as 196.36 kilonewton. Now, second thing, we need to calculate the value of the design strength due to rupture of critical section. Rupture of critical section. Now, to calculate the rupture of critical section, we need to connect, or first we need to calculate that ANC, the net area of the connected leg, and the gross area of the outstanding leg, because we just seen that the design strength due to rupture of critical section for the single angle section, we can calculate this by using this formula, where this part considered the ultimate strength or the rupture of the connected leg, and this part will consider the yielding of the outstanding leg due to that shear leg effect, and beta that cater for the shear leg effect. So first we need to calculate the ANC. What should be the net cross-sectional area of the connected leg? So net cross-sectional area, what was the gross cross-sectional area? AGC, gross cross-sectional area, just 90 minus 6 by 2 into 6, right? So what will be the net cross-sectional area? We just made one hole over here. So just reduce the hole diameter. So 90, that is the total leg length, minus the hole diameter 18, minus that 6 by 2, because we are considering up to this part. Why? Because if we consider up to the last part, we have a overlap zone, and our estimation will be higher than the actual value. Okay, now what will be the gross area of the outstanding leg? It is nothing but 60, the total width, and we need to come up to the center point. So 60 minus 6 by 2 multiplied by 6, so 342 mm square. So we have the value of ANC, we have the value of AGO. Now we need to calculate the value of beta. For calculating beta, some parameters we need to know. Okay, to calculate the beta, one more parameter, LC, which I forget to explain. What is the LC? This is the length of the connection. Length of the connection. This is measured from the center of first bolt to the center of last bolt. What is the LC? This is nothing but the length of the connection, which is which is calculated from the center of first bolt to the center of last bolt. So if you have the number of bolts, and if you know the pitch distances, then you can calculate the LC. Okay, so let's calculate the LC for this. So tell me, what will be the LC for this connection? We have one pitch length, two pitch length, three, and four. So we have four pitch length over here, and each pitch is 50 mm. So what will be the value of LC? Quickly tell me, what should be the value of LC for this connection? बताओ quickly. The pitch distance is 50, and we have 1, 2, 3, 4 pitches. What should be the value of LC? Quickly. Hello? Just add the pitch distances. 50 plus 50 plus 50 plus 50, or we can write 4 into 50, that equals to 200 mm. Yes or no? Right? Okay. So here these things are given. Length of the connection. So LC is nothing but 4 into 50. Then FU, this is 410 plate. So FU will be 410. What is the value of FY? That is 250 MPa. Now, what is the value of BS, shear lag length? So here the bolting is done. So we need to consider the length from this to this, right? So that will be equals to 60 plus 90 minus total thickness 6. So that comes out as 104 mm square. Sorry, this will be mm. It's a length. So that's come as 104 mm. Okay. Now what will be the W value? What will be the W value? It is the width of the outstanding leg. So for this case, 60 will be the outstanding leg. So put all these values here. W is equals to 60, T is 6 mm, Fy 250, Fu 410, Bs is 104, LC is the length of the connection that is measured from the center of first bolt to the center of last bolt, and that comes as 200 mm. So put all these values. The value of beta is coming as 1.159, which is greater than 7. That means okay. Now we need to check against this criteria. So this value fu by fy into gamma m naught by gamma ml comes as 1.433, which is also greater than the value of beta, which is calculated using this equation. So finally we can consider that beta value will be equals to 1.159. Now we can calculate the design strength due to rupture of critical section. So just put all these values in this equation here. 0.9 ANC value we have 414 mm square. AGO value we know 342. Beta value 1 point, what that comes, beta value comes as 1.159. So 1.159, what is the equation here? 159. So if we plug this and solve this equation, you will have the value of TDN. Okay. Now one more thing we need to calculate here is the design strength due to block shear failure. Block shear failure. Now it is an angle section. So generally this kind of block will come out like this will be my shear plane, and then the tension plane will occur along this side because the outstanding leg is on the other side. So it is less likely phenomena that this this side will get ruptured. So we will have this kind of block that will come out. So here what is the shear plane? This is the shear plane because this is the parallel to your applied load. And what is your tension plane? Along this plane, this is the tension plane. So now you can calculate the AVG, the gross area along the shear plane. So what will be the gross area along the shear plane? So what should be this length? This length will be up to the center of this bolt. So 30, that is the end distance, 30 plus 50 plus 50 plus 50 plus 50. So 30 plus 200, that will be the length multiplied by the thickness 6 mm. So that comes as 1380 mm square. Now what will be the net area along the shear plane? So how many bolt hole we need to deduct? 1, 2, 3, 4 and half. 4 and half shear plane. So 230 is the total length from here to here. 30 plus 200, 230 minus 4.5. Why 4.5? Because we need to deduct 4.5 bolts to get the net area in shear plane multiplied by 6. So this is your net area in shear plane. Now for the tension plane, this is 40 mm. So gross cross sectional area will be 40 into 6. 6 is the thickness to 40 mm. And net area, how many bolt hole we need to deduct from the tension side? This is the half bolt hole, half bolt hole. So 40 minus 0.5 into 18 multiplied by 6. So the net area and gross area we have calculated. Now just put in these equations: shear yielding and tension rupture, and tension yielding and shear rupture. So first thing, shear yielding and tension rupture. If we plug all these values in this equation, the TDB or TDB1, you can more precisely say TDB1, that value is comes as 235.98 kilonewton. Now for another case, shear rupture and tension yielding. So shear rupture and tension yielding, that TDB2, we can write it down 0.9. Look at this shear plane. We have considered the rupture along the shear plane and yielding along the tension plane. So if we plug all these values, this is coming as 206. So obviously what will be the TDB value? Will be minimum of your TDB1 and TDB. So 206 kilonewton. Now we can calculate the design strength of this angle section. So design strength of this angle section will be minimum of TDG, that is the design strength due to yielding of gross cross section. TDN, if we plug all these values in the rupture formula, then you will get 212.29 kilonewton, and for block shear failure this comes as 206.91. So obviously look at this, the yielding failure is the failure criteria for this angle section. So what will be the design strength for this? 196 kilonewton. Clear? So by this way we can calculate the design strength of a tension member for plate and for single angle sections. Now the thing is how, or for this was for the bolted connection. Now if we have the welded connection, wire welding is used to make the tension member. So this is the example, NPTEL example. That example is provided on your course material of this week. So I will discuss with this example. So here what will be the different? What will be the different? Like we have here 19 to 16 to 6. This angle is connected by 10 mm thick, connected with 10 mm thick gusset plate by some fillet welding. So what will be the different the difference in calculation? What will be that? First thing, we did not make any hole. That means the connected leg and outstanding leg both will have the gross area, right? And secondly, when we will calculate the BS, the shear lag length, what we have found for the welding connection, it will be the width of the outstanding leg. So let's quickly solve this example. So what will be the gross area of the connected leg? It is 19 to 16 to 6. So this is the connected leg A and C. Because we cannot write the net area here, so that will be the gross area of the connected leg. 90 minus 6 by 2 into 6, because we did not make any hole, so we just need to consider the whole area from here to center up to here. So that comes as 522 mm square. What will be the gross area of the outstanding leg? So the outstanding leg length is 60 mm. So we have just discussed how to calculate these areas. So we just need to come up to the central line. So 60 minus 6 by 2 into 6. So this is our two areas. One is the gross cross-sectional area of the connected leg and the gross cross-sectional area of the outstanding leg. So first we need to calculate the design strength due to gross cross-sectional area or yielding of gross cross-sectional area, and this can be found out by this formula. TD is equals to Fy into Ag by gamma m. That Ag will be your NC plus AGO, total gross sectional area. Okay, so if you sum them up, that will come as this, or directly you can calculate this AG value from the SP6. Okay, or I will suggest that you should calculate the value, or you should learn calculating these values using directly from this equation, because these codes are not available here. So if we add these two values, I think that will comes as 522 plus 342, 860, 864. So here 865 is considered. I think this value is taken directly from the SP6, that's why it will have. So you can consider 864 also, no problem. So the TDG value comes as this. What will be the rupture strength? So for rupture strength we need to calculate the beta value, and now to calculate the beta value we need to find out the BS, the shear leg length, LC length of the connection, and W. So what is the BS for the welding connection? We have already known that the for welding connection we need to consider the width, whole width of the outstanding leg as the value of BS. So here the outstanding leg length is 60 mm. So BS is considered as 60 mm. What is the value of this T? T is nothing but the thickness. What will be the value of LC? Length of the connection. So here we have to consider the average length. Average length. So here we have 75 mm and here we have 75 mm. Like we may have the connection like this, where the two part have two different length of welding. Like here I have done full welding and here I have done only welding up to this. So for that case also we need to consider the average length as the length of the connection. So here symmetric section is there. So what will be the average length? 75 plus 75 by 2. And in the case of bolted connection, the LC value was the center to center distance between first bolt to last bolt. So if we put all these values, the beta value is coming as this. And when you have found out the beta value, you just need to put all these values in the equation of TDN. So if you put all these values in TDN equation, you will get the design strength due to rupture comes as 234 kilonewton. Also, alternatively, like I have already said, for the case of primary sizing, where you don't know how many bolt hole are there, or what should be the area and all these things. So this primary sizing formula, by this formula you can also calculate these things, because in this case what is happening here, precisely what is happening here is no bolt hole is made. So here, using this primary sizing formula, this comes as 226 kilonewton. Now we can calculate the strength due to block shear failure. So for the block shear failure, here it is easy, because this two plane will be my shear plane and this plane will be my tension plane, and we don't need to deduct any bolt hole here. So my gross cross sectional area along shear plane and gross cross sectional area along the tension plane will be same. So what will be the gross cross sectional area along the shear plane? It is nothing but 2 into 75 into 10, because 75 is the total length, 10 is the thickness of this plate, and 2, because we need to consider two sides. AVN, that is the net area, we don't need to deduct any bolt hole here, so that will be same. What will be the value of the gross cross sectional area along the tension plane? So that will be your tension plane, say AB will be the tension plane, because this plane is perpendicular to the application of load. So 90 into 10. So if you put this equation TDB1, first look at this, the shear plane get yielded, or we have considered the shear yielding and tension rupture. So this comes as this 462 kilonewton, and when we consider that shear rupture and tension yielding, this comes as 460 kilonewton. So here we can consider, or we can calculate the value of TDN. So what will be the design strength of this connection? Minimum of, we have calculated the TDG value, that was I think 196.6 kilonewton. Yes or no? Yes, 196.6. Now what was our TDN value? We have considered this 260 or 234, whatever you want. Then we have the block shear strength as 460. So obviously this 196.6 kilonewton, the design strength due to yielding, will be the strength governed for this kind of connections. By this way, so we have learned how to calculate the design strength of the tension member for plate section as well as for the angle sections. Now the next thing is how to design this connection, how to design it. Here, for the previous examples, the arrangements were provided, the number of bolts were provided, the angle section were provided. Now, if we need to design them, like we just have, the idea that we have a gusset and we need to connect some angle over here by using bolts or weld to transfer some amount of load, say 100 kilonewton. So how we can design this section? What should be the steps? We don't know what should be the size of this angle, what should be the size of the bolts, how many bolts should we provide. We don't know, we don't have any information. We just have information that we need to transfer some amount of load, and we know that if we need to make a tension member between gusset and plate, or gusset and angle, what should be the mode of failure criteria? So what should be that? First we need to select this angle section, what should be my angle section. Then we need to select some suitable bolts. Then we need to calculate the number of bolts. So how we can calculate that, or how we can find out this section? So first we need to consider that TDG value as the yielding value or as the failure criteria. So TDG was AG into Fy by gamma m naught. So first thing we will consider that this connection will fail in yielding. So TDG, so here 100 kilonewton. So if we equate it, 100 into 10 cube is equals to say AG into, we have used plate 410, so 250 will be the yield strength divided by 1.1. So from here we can have the AG value, the gross cross-sectional area required for this angle section. So we have say AG like 1200 mm². Now, with that AG, we need to go to the SP6 to find out that which angle section the cross-sectional area is, matching this value, or, have higher value than this. So from there, we can find out the angle section. Now, while we have, select the angle section, now we need to calculate the bolt, number of bolt required. So first, we need to calculate the design strength of bolt, shear capacity and bearing capacity. So if we know the bolt strength, say for example, the bolt strength is 30 kilonewton, the shear capacity is the strength of the bolt. So how many bolt we will require? Just T divided by VB. So nearly equals to 4 bolts we need. So now we have the section, we have the bolts. Make the arrangement. Arrange kar do with suitable pitch and edge. Now the thing is, we have made the design, right? First step, we have, select the section. Second step, we calculate the number of bolt. Now we need to check against we have, design against the yielding. So we need to check against the rupture and block shear failure. If your arrangement and the section, whatever you have selected, that matches this criteria, then your design is safe. So let's quickly go to that step, what I have just said. So first we need to calculate the gross cross-sectional area required to carry the given load TU. That means one factor tensile load is given. So to counteract this load, first we need to calculate the gross cross-sectional area considering the yielding as a failure. So here we can have the gross cross-sectional area, like, I have made a calculation here. So by this way we can have a gross cross-sectional area. Then we have to go to SP6 to match or to find out the value of that or the section size. We have to select the section size. Okay, now what should be the second step? The second step should be the design of bolts. That means first, if the grade and dia of bolt is given, then we have to go with that bolt. If the dia and grade of bolt are not given, we need to consider the dia grade first. Then we need to calculate the shear capacity of bolt and bearing capacity of bolt. So we have that VB, the strength of bolt, will be equals to minimum of shear strength VSB and BDPB, minimum of that. So when we have that VB value and we know that TU, that maximum tensile force we need to transfer, just divide by VB, we will get the number of bolts. Now when we made the arrangement, what should be the step 3? Step 3 should be, we need to check against rupture and block shear failure, because we have made the design considering the yielding as a failure, but we have seen that two more failure can occur. One is yielding, one is rupture, and second is block shear failure. Lastly, we need to check for slenderness ratio. We have seen in table 3 what should be the slenderness ratio for that particular member which we are going to design. So let's quickly go through one design example so that this thing get clear. So here this is the example that a tension member 3 meter long carries a factor tensile force 200 kilonewton. That means we have the factor tensile load 200 kilonewton. Then design a suitable single angle section with 20 mm diameter of bolt 4.6 grade. Bolt there that the bolt diameter is 16 mm and grade of bolt is 4.6. Also some data is given, like assume the longer leg is the connected leg. Longer leg is the connected leg. Okay. So here let's step by step quickly solve this problem. So factor tensile force is given 200 kilonewton. Diameter of bolt is given. Diameter of bolt hole we can calculate. Grade of bolt is given 4.6. So from the grade of bolt we can already we can easily calculate the ultimate tensile strength of bolt. So grade of bolt is 4.6. What will be the ultimate tensile strength of bolt? Nothing but 400 MPa. If Uy, the yield strength of the bolt, that is also can be calculated from the grade of the bolt, and the length of the connection is given as 3 meter. So these values are given. The first thing what we need to do, we have to select a suitable angle section based on the criteria of yielding failure. So here we have considered first step, design of the section or selection of the section. You can write it like that, design of the section or selection of the section. So first we have considered the yielding strength. What was the value of yielding strength? That TDG is equals to AGFY by gamma M naught. Now that TDG we have equate with that TU, that ultimate tensile strength. So TU is equals to AGFY by gamma M naught. So what will be the value of AG? AG will be TU, the ultimate tensile load acting on this member, into gamma M naught. So here I made it convert it to Newton and then 250. So here the gross cross-sectional area required to carry that 200 kilonewton of load comes as 880 mm square. Now we need to select one angle section according to that, or which will match the gross cross-sectional area of 880 and more. So go for the SP6. So here is the screenshot of SP6. You can see here that IS is 75 into 50 into this is the thickness. So I have selected 75 into 50 into something. You can select 100 into 75 into something. So here look at this. If I select this section, which thickness will match my value 800 or something and more. So here if I consider 75 into 50 into 10, then the gross cross sectional area is 1152 mm square, which is greater than 880 or 882, whatever the area which is we have calculated from the yielding of gross cross section. So I have selected that angle 75 into 50 into 10 from this, and also for this angle section the IXX value, least radius of gyration value, all these values are provided in this clause. So here I have selected that from SP6 page number 12, I have selected 75 into 50 into 10. Now here the gross cross sectional area is this, which is more than my 880 value, which is required to transfer the 200 kilonewton of load. So that from this table we have found out the value of least radial dimension, or we can say least lateral dimension, R minimum, which will required when we will check for or check against the straightness ratio. So now second step, we need to design the bolt. So we have selected that angle section, that my angle section will be what was the value, 75 into 50 into 50 into 10. Now we need to calculate how many bolts will be required to transfer that TU is equals to 200 kilonewton. So we need to calculate the shear capacity of bolt. So here how many shear plane will be there? One shear plane will be there, and I have considered that shear plane is passing through the root because that will be the most critical case. So this part will get 0, and there is no correction factor required because neither this is a long joint nor it is a large grip, neither packing plate is there. So NN will be 1. So the value of VDSB will be equals to 43.3 kg. Now we need to calculate the bearing capacity of the bolt. So what will be the bearing capacity of the bolt? So to calculate the bearing capacity, we have the formula 2.5 kb dt fu by gamma m naught. Here we need to consider pitch and end distance. So let's consider pitch is equals to the minimum pitch criteria, that is 2.5 into d. Here d is 20 mm, so 2.5 into 20. So we will consider 50 mm as pitch. And edge and end distance, we have considered the minimum 1.5 d naught. You can consider 1.7 d naught also for the design. So that comes as 33. So we have considered let 33 for now, then we will later on we will increase to 35. So here we can calculate the kb value. We have calculated lot of times the kb value. So when we have the kb value, we just need to put all these values, and the v wave, the design strength of bolt due to bearing failure comes as 82. So what will be the strength of the bolt? Obviously, the shear capacity of the bolt will be the strength of the bolt, that comes as 43 kilonewton. So how many bolts we need to make the joint? So we have 200 kilonewton of load to get transferred, and one bolt can carry 43.5 kilonewton of load. And how many bolts we need? We need 4.4 bolts, nearly 5 bolts. So now we have 5 bolts. We have considered pitch is equals to 50 mm, edge and end distance is equals to 35 mm now, and we have ISA 75 into 50 into 10. So we have made the design. So make the arrangement. So here the longer leg is connected, and this is your 20 mm dia bolt of 4.6 grade, and we have 4 bolts. So we have arranged these bolts 1, 2, 3, 4, 5 with a pitch distance 50 mm and end and edge distance as 35 mm. So we have designed that connection. Now we need to check. So we have designed this connection based on the criteria of yielding failure, Now we need to check my connection against three things. First, with respect to TDN, that means design strength due to rupture of critical section. Secondly, due to block shear failure TDB, and thirdly, against the slenderness ratio. So now we have the arrangement, and we know how to calculate the TDN value. We just solve some problem, and how to calculate TDB value. So just quickly solve this. So here design strength due to yielding we have already calculated, and we have considered this section from here. So obviously this value will be more. Now two more thing, here we need to calculate the design strength due to rupture of critical section. So rupture of critical section formula, that connected leg will reach up to the ultimate strength, and the outstanding leg will reach up to the yield strength. So you just need to calculate the beta value, ANC and AGO value. So just I have calculated these things. Now you can, I think you can calculate this here. So I'm not going line by line. Then by this way you can calculate the value of TDN. So TDN value is coming as 275.37 kilonewton, which is more than 200 kilonewton. That means this connection, the rupture strength of this connection TDN is equals to 275.37 kilonewton comes as, which is greater than the amount of load this connection need to transfer. What was that? 200 kilonewton. That means this is safe. Now you need to check against the block shear failure. So here you have this plane as shear plane and this as tension plane. So just calculate AVG, the gross area of the shear plane. What will be that? So what is the total length from here to here? 200. This is the LC value, and 35. This is the end distance. So this is 235 into 10. Now VN net area, we need to deduct how many bolt hole? 1, 2, 3, 4 and 4.5. So 4.5 into this. So you can calculate these values and put these values in this equation. So you can calculate that my TDB value comes as 311. The block shear strength of this connection, whatever I have designed here with the 5 number of bolts and ISA 75 into 50 into 10, this can have a block shear strength of 311 kilonewton. That is also greater than TU value, right? That means whatever I have designed with respect to, first we have considered that yielding is my failure criteria with respect to yielding. Now we can say that this connection is safe against rupture and block shear also. Now one more check is needed, that is the check for the slenderness ratio. So this is a connection of a roof tie. So for the roof tie of a truss member, we consider 350 as the maximum slenderness ratio. So what will be the maximum slenderness ratio for this? Lambda is the effective length divided by least lateral dimension. So what was the effective length for the member was 3 meter. So 3 into 1000 millimeter into 10.6. That was the R minimum for ISA 75 into 50 into 10. From where you get this? SP6. That means in all respect, my design, whatever I have make this design, this is safe. So by this way, we can design one tension member. So this is not a straightforward process. This is a iterative process. First thing, we have to select one section, then we have to go step by step. Then again, if the criteria and all these things has matched, then it's okay. Otherwise, we have to select another section with higher cross sectional area, and we have need to follow the steps. Then check wherever this section can withstand that load or not. Okay, so that was the design part. Now quickly solve some examples or assignments regarding previous year questions. So do you have any questions regarding the concepts which I have covered regarding the design tensile strength, how we can calculate for a plate section and for a angle section, how we can calculate the design strength for a bolted joint and for a welded joint, how we can calculate the design strength when that staggered bolting is there, and how we can design this kind of connection. So I think you have some idea of these things, how we can deal with the tension member. Yes or no? Yes or no? Okay. So let's quickly solve the examples, previous year example. What it says, the first example, a circular bar of effective length 2 meter is used as permanent tension member other than pre-tension member. So minimum diameter of the bar should be, what should be the minimum diameter of the bar? So how we can calculate it? So first thing, you need to check what kind of tension member is this. This is the permanent tension member other than pre-tension member. So what should be the value of the slenderness ratio? 400. Member always in tension other than pre-tension. So 400 should be the maximum slenderness ratio. Slenderness ratio. Okay. So we have that lambda max, maximum slenderness ratio, is equals to 400. Now what we mean by say slenderness ratio? Slenderness ratio is the ratio of the effective length upon least lateral dimension. Least lateral dimension. Okay, so what will be the value of that? So if we equate this equation, so LE is equals to R minimum into this. So we have R minimum is equals to, we have a formula, LE by lambda max. LE by lambda max. So what is the value of LE? 2.4 meter. That means 2400 mm divided by 400. That means 6. So we have R minimum. R minimum is equals to 6. Now tell me, what is the value of R minimum? The radius of gyration. Radius of gyration for a circular section. So what is the radius of gyration? How we can define radius of gyration? So radius of gyration can be defined as the distance from the axis of rotation at which, if the whole mass of the body is concentrated, the moment of inertia will be same. That means we can write it like K. From our song knowledge, we can write it down I upon A. So what is the value of I for, what is that K? K is nothing but the R minimum or least radius of gyration. What is the value of I for a circular section? What is the value of I for a circular section? Pi into d to the power 4 by 64 divided by, what is the area of the circular section? Pi by 4 into d square. So if you simplify these things, what you will get, K or R minimum will be equals to d by 4. So we have R minimum value as 6. So just d by 4 is equals to 6. So what will be the value of the diameter of the circular section? 6 into 4, that means 24 mm. Clear? So this is the 24. Now go to the next question. What it says, for block shear failure, a tension member, the failure occur along a path through the connection involving. So we have just seen that involving two planes. One is shear plane and one is tension plane. So this is P. So tension plane, tension in one plane and shear on other perpendicular plane. Obviously, so one will be the correct, and the shear plane, the plane which are parallel to the applied load. So here 1 2 will and 3 4 will be the shear plane, and 2 4 at the perpendicular plane, that will be the tension plane. Now what is the third question says? Third question says, for primary sizing, the rupture strength of a net section can be approximately taken as TDN is equals to alpha n Fu by gamma ml. What will be the value of alpha for 5 volts? What is the value of alpha for 5 volts? What he says, for 4 or more volts, for 4 or more volts greater than or equals to 4 volts, what is the value of alpha? 0.8. So 0.8 will be the correct answer. Now let's come to the second question. The design tensile strength of a single angle section due to rupture of critical section. क्या देखा हम लोगों ने? The connected leg will reach up to ultimate strength, and the outstanding leg will reach up to the yield strength. That means we are considering the rupture at the connected leg. So look at where the rupture is considered at connected leg, 0.9 ANCFU, and yielding at the outstanding leg, A0 Fy by gamma m naught with beta A factor, which will cater the shear leg effect, which I have discussed previously during this session. So B will be the correct answer. Yes or no? Now question number 5 says, what is the shear leg width of 100 into 10 in 100 into 100 into 10 in case of bolted connection? So you need to calculate that BS value. So what is the BS value for the bolted connection? What I say, from the center of this bolt to, you need to go up to the end. So what will be the value? So 50 minus, what is the thickness? 10 by 2. 10 by 2. That means we have come up to here, right? Plus, from the center we need to go up to last. So 100 minus 10 by 2. So that is the total length. So what is coming as? What is coming as? 100 plus 50 minus 10. So 140. Or you can directly use that codal formula, W plus Wy minus T. What is the W? That is the width of the outstanding leg. The what is Wy? This is the length from the center to the end of the connection. So either you can use this, and I have used this formula because using this we will get W plus Wy minus T. But I have explained, and we have learned about the shear leg length. Clear? Yes or no? Now tell me, for the welded connection, what will be the length of the this? If say for example, if there is not bolting is there, only welding is there, only welding is there, only welding is there. What will be the value of BS for this thing? Tell me quickly. Only welding is done. What should be the BS value? W. Yes. W means that is the width of the outstanding leg. Width of the outstanding leg. So this is 100. Okay. Now come to question number 6. What question number 6 says? A single angle section 19 to 16 to 8 is connected with a gusset plate with 3 bolts of 14 mm diameter in one line at a pitch. Pitch बोल दिया गया. Pitch is equals to 50 mm. Beta value is given also. No. You need to calculate the beta. You need to calculate the beta. Okay. You need to calculate the beta and consider that the longer leg is connected. Okay. So let's calculate the beta, no problem. So 90 leg is connected. We have 3 bolts with pitch 50 and end distance is given. No, don't need the end distance. Okay. So beta, what is the formula for beta? Calculate beta value. What was the formula for beta? 1.4 minus 0.076 BS by LC W by T into Fy by Fe. So we need to calculate the BS first. What should be the value of shear leg length? So BS value will be BS will be directly will use W plus Wi minus T. So what is the value of W here? W is 60 so 30 plus 60 minus 10, that comes as 82 Clear? What is the LC value? We have 3 bolts. We have 3 bolts with pitch 50. So what is the value of LC? LC is the length of the connection. It is the distance from the first bolt to the center of last bolt. So what will be that? 50 plus 50, 100 Now, what will be the W value? It is the width of the outstanding leg, 60 Now put all these values in this equation. So the value of beta comes as, from this equation, 1.115. So which is greater than 0.75? Now we need to check against this criteria that beta should be less than this value. So this value comes as 1.44. Obviously my beta comes as 1.115, which already we have solved this problem while solving that example 1 or 2. I think example 1 of the angle section. Clear? Okay. Now for the same example, or this is okay, this is another example. What this says, an angle section Fe410 grade steel, or the net area is given 938, is connected to a gusset by 3 number of bolts provided along the length in the end connection. Calculate the approximate value of the rupture strength. Okay, so we need to calculate the rupture strength due to primary sizing. Okay. Here the primary sizing is mentioned. So for the primary sizing, code says TDN should be equals to alpha into AN FU by gamma M. What is the value of AN? This is given here, the net area 938. Okay. What is the value of alpha? This will depend on the number of bolts. So here we have 3 bolts. So for 3 bolts, what code says? If we have 3 bolts, 0.7 will be the value of alpha. So the value of alpha will be 0.7. And Fu 410, gamma ml 1.25. Okay. Now this will come as Newton, and if we multiply it with 10 to the power minus 3, you will value in kilonewton. Clear? So TDN value comes as 215 for primary sizing, or when we consider the primary sizing. Now move to next question. An ISA 100 into 75 into 10 is connected to a gusset plate through its longer leg by 3 bolts of 20 diameter and 4.6 grade in a line. Pitch is given as 55 Okay, so we have 3 bolts, 1 2 3, with pitch is provided, that is 55 Okay, one more thing is provided, end distance is provided. Okay, pitch provided, edge and end distances, look at this, edge and end distance is provided. So E dash is provided as 45 and E is provided as 30 So that means this value is 45 and this value here is 30 Now they have said the calculate calculate the values of minimum gross and net area along the shear and tension plane. Okay, so let me draw this in a bigger picture so that we can have a better understanding. So what this the problem says we have an ISA, Indian Standard Angle Section of 100 into 75 into 10. Okay, where 3 bolt hole are there. So here, tell me which should be the shear plane. Obviously, this plane will be the shear plane. Yes or no? This is the application of load. So this will be the shear plane. So what is the value AVG? Total gross cross-sectional area along the shear plane. What will be that? We need to calculate the total length. So this end distance is 30 and pitch distance is 55 and 55. So what will be the value? 30 plus 55 plus 55, right? Into what is the thickness of the plate? 10 mm. So what is the value? AVG 1400 mm square. Now tell me what is the value of AVN, net area along the shear plane. Obviously this will be your shear plane because this plane is parallel to the application of load. So what will be the value of AVN? We have along our shear plane we have 1, 2 and half of 3. This 2.5 bolt is there, and this length, this total length is nothing but 30 plus 2 into 55. So what will be the AVN value? VN is nothing but 30 plus 2 into 55 minus how many bolt hole we need to deduct here? 1.5, sorry, 2.5 number of bolt hole. So 2.5 into diameter of bolt. Diameter of bolt is given as 20 mm. So what is the diameter of bolt hole? 22 mm multiplied by the thickness of the plate. Okay, so this comes out as 850 mm square. Okay, so AVG, the gross cross-sectional area along the shear plane comes as 1400 and the net cross-sectional area along the shear plane comes as 850. Now we need to calculate 2 more areas along the tension plane. So what will be the tension plane? What will be the tension plane? This plane. This plane. So this plane will be the tension plane, right? So the distance from here to here, the edge distance is provided at 45 mm. So what will be the gross cross-sectional area? Gross cross-sectional area ATG along the tension plane. Why this is tension plane? Because this is perpendicular to the load and we have discussed how this tension plane is occurring here. So nothing but 45 into 10. What should be the net area? We need to deduct only half the bolt hole. Half the bolt hole. So 45 minus half the bolt hole into the hole diameter. So now check which option is matching with your answer. That will be the answer for this question. Now what is the next question? Okay, here the next question says with the welding connection or welded connection. So we have discussed how to calculate the design strength uh, when the welding connection is done across the angle section. So let quickly recapitulate the things again. An ISA 19 to 16 to 10 is connected to a 10 mm thick gusset plate by 8 mm fillet weld. Calculate the design tensile capacity of the angle section either governed by yielding of gross or the rupture of net section only. That means we don't need to consider or calculate the TDB value. So the gross cross sectional area and beta value is given. So we just need to calculate the TDG and TDN value. So what is the value of TDG? TDG, that is the design strength due to yielding of gross cross section. Fy into Ag by gamma m naught. The Ag value is given 1401. So plug these values 250 into 1401 divided by gamma ml 1.1. This is Newton, and if we divide it by 1000, this will come as kilonewton. Okay, so here the calculation is given 318. Now what will be the design strength due to rupture of critical section? TDN. So TDN we have to calculate 0.9 FU ANC by gamma ml plus beta. That means the rupture at connected leg and yielding at the outstanding leg. So beta into AGO Fy by gamma m naught. So the beta value is provided 1.29. We need to calculate the value of ANC and AGO, right? So what is the value of ANC? Here no bolt hole is made. So what is the value of the gross cross sectional area of the connected leg? ANC will be nothing but we need to consider the area from top to the center. So ANC will be 90 minus 10 by 2. That means we need to come up to the center line into the thickness 10. So here this is given 90 minus 10 by 2 into 10. So we just need to come up to this section. Like if we make the angle section bigger, so we just need to come from the top to the center. The total is 90, and if I need to connect up to the center, if the thickness is 10 mm, so 90 minus 10 by 2, that will be the width of the connected leg or net width of the connected leg multiplied by area. Now why we are deducting this thing? Because we are calculating the area first separately, then we add them up. That's why. What will be the gross area of the outstanding leg? Nothing but 60 minus 10 by 2 into 10. So now put all this equation in this value. So you will have the TDN value 412, TDG value 318. So what will be the strength of this kind of connection? What will be the design strength? Obviously the TDG value. That means 318.43 kilometer. 318. So that means my C option will be correct. So the range from 315 to 320 will be the design strength for this kind of connection. Okay. Okay. So that's all. If you have any doubts, then you can raise or any questions, or else we can conclude the session here. So do you have any doubts or questions, or you have understood these things? You can actually you can unmute yourself. Okay, let me unmute you. Okay, so do you have any questions, or we can end this session? Okay, no doubt. Varun? So I think if you go through this video lecture again, you will able to solve all the assignments, I think, regarding this week also. Okay, so then I will end this session. Okay, okay. Thank you. Good night. Okay, how can we calculate effective length by using minimum radius of gyration? Okay, how we can calculate the effective length from the minimum radius of gyration? Nothing. It's like very simple. Like if we have one member where the lambda max. So lambda max is equals to effective length by r minimum. Now you need to find out this lambda max. If we know that lambda max, say for example 400 for direct tension member and LE by R minimum. So you can calculate the LE value if the R minimum radius of gyration is given. If LE is given and the cross section is given, R minimum can be calculated. Like the circular problem which I have solved little later, a little sometimes back, this problem. So what you are asking is nothing but you just need to find out that lambda max value, which will be LE by R minimum. right? If your section is a rectangular section, then R minimum will be nothing but you can calculate it root over I by a. For a rectangular section, the I will be, what is the value of I? Pi d cube by 12, and a, so by this way you can calculate the value of LE or R minimum, vice versa. Clear? First, you need to identify which is the maximum value of lambda. If you can calculate the lambda value, then you can calculate the R minimum. Yes or no? Just follow this example. Okay. So, do you have any doubt? Any more doubt? Okay, then we will conclude here. Good night. We will meet on the next Monday. Good night.